Good morning. Let's see, let me get all the things. Chat. There's the attendance form, as usual. Go ahead and fill it out when you have a sec. There was something else I wanted to say as well. I don't remember what it is. Oh, I know what it is. This is a reminder to everybody. There's also online drop-in tutoring with student tutors available. If you're looking for more help and I'm not available or other people aren't available, you can get help from student tutors here. I can type. Sure. Right there. So that's another resource available to you. I encourage you to use. They have lots of availability. So go over there. You can schedule an appointment with them for whenever. Let's see what else. So I know Pham has a midterm coming up this Friday. I think Friday, right? Yeah. And so I guess I will say, first of all, I'm planning on posting some sort of practice midterm or study guide this afternoon. And then also trying to make video, instead of posting solutions, I think I'd rather make like videos of me going through the solutions. So I'll try and do that and get that up sometime today or tomorrow. So look for that later today. I will definitely send out an email once I have posted the, I'll call it the study guide. And I'll try to make it so it's, because I've got Pham's midterm review up here, and I'll try and make sure I address kind of most of the things that he's got on here. I don't see any, let's double check here. Yeah, I don't see any, so it looks like the only method of integration that's on his test, that's like, you know, one of the more hard ones is use substitution. I don't see integration by parts on his test or on his midterm review. And I don't see any partial fractions or any of that kind of says. So he says, sure, yeah. So that's what I see on there. I will try to make a practice test kind of thing that covers this stuff and nothing extra. I definitely see volumes for disk and washer, so I'll try and get some of that. Okay, so I guess I should say, do you guys have any questions specifically for the people in Pham's class first, since you guys have a midterm coming up? I know Merck's also has was supposed to have a quiz yesterday, but it got postponed, so we can certainly get to the Merck's people as well. But are there any Pham students who have specific things you would like to ask me about? Annuity, sure. So just before I guess that, which I'm certainly happy to, are you guys permitted, is your exam on Friday, is it going to be open note or is it going to be like closed note, you don't get anything? All right, and he's using Examiny, right, to actually like proctor it. Okay, so you guys actually have to like remember the stuff. Okay, well, that's a lot of formulas. Ugh. All right, trashed. Okay. So yeah, we can talk about annuity. So jeez, I don't know the annuity formula. I'm sure it's on this list here. Who would ask about that? Sorry, let me see if I can find it. I thought I saw it on here. I see the compound interest formula. I see derivatives. We can definitely do more use subs as well. He's giving an equation sheet. Okay. Well, I have to imagine. I would like to imagine. I guess I don't have to imagine. I would like to imagine that a rational person, if they're going to ask you about annuities, wouldn't be so foolish as to expect anyone to memorize the annuity formula, because that's ridiculous. But yeah, we can definitely talk about all those things. So let's talk about disk washer. So yeah, Let me write these down just so because the chat will go away eventually, or not away, but it'll move. So I got annuity here. And let's see, where'd you go? Sorry, one sec. U subs for sure. Average value. Dishwasher. And along with annuity, let's also talk about the surplus and the other one, consumer surplus. And I forget what the other name is, consumer something. I've got it in my book here. Sorry, and producer surplus. We can definitely talk about both of those as well because I feel like they're kind of in the same vein as annuity. So let's see. So let me erase some stuff here. You see my board all right. And I'm getting low on my pens, unfortunately. I'm kind of down to the orange pens, which show up fine, but they just erase really gross. Like I feel like the other ones, when you just don't see the other ones, but the orange ones especially, you just see like the orangeness everywhere. Okay. All right, let's see here. So annuity. So hopefully he'll give you the formula. Here it is. So the future value, right? So annuity is like you're investing some amount like every year and you kind of get some amount at the end. So here is what it looks like. The future value of an annual income. So C of T. Oh, sorry. C of T. I should enlarge this. That's hard for me to read. Make it bigger. Yeah, that's much better. Okay. Let's see. So we have C of T. So C of T. So if you're making C of T income per year, or each year, I should say, then after T years, capital T, we have that, sorry, where'd you go? The integral from 0 to capital T. So capital T is a constant, or some set value, I should say, of C of T e to the negative RT. Where R is the continuous rate. So honestly, to me, this sort of question is, you're going to get the information, right? He's going to tell you hopefully what the function is, what the time is, and you're just going to kind of throw it into this integral. And hopefully C of T is constant because that's going to make it not terrible. If C of T is some function, you're probably going to have to, oh no, we don't do integration by parts yet. So C of T is probably going to be constant or something that makes it not awful. Let me see if I can find a quick problem here because I wasn't expecting annuity. Just one sec. Come on, annuity. Sorry, one more. Okay, I'm going to start looking at the wrong book. Got like 5 books here. Actually. Okay, so let's look at something like, yeah, so all the examples in the textbook have C of T being a constant value, so that's a good sign to me. It means it's probably not going to be absolutely terrible. So let's say we have the following. So we're given C of T is equal to $250. Just for your reference, this is problem 81 from section 5.4, in case you're interested. Oh, also, yeah, sorry, this is where R is the, yeah, I can see why you might not be able to read that. Where R is the continuous rate. Sorry about that. Also, I should give you guys the attendance one more time, just one sec. Okay, yeah. So here's what we're given in this particular problem, 81 from section 5.4. The amount of money you're making every year is $250, constant. R is 8%, which we're going to change to 0.08. And then T, capital T, is 6 years. So if we're given all this information, it shouldn't be terrible to have to do this. We're just going to put it all into this formula. We're going to go 0 to T, C of T, e to the negative RT. So we're going to go, our annuity is going to end up having integral from 0 to 6, C of T, times e to the negative R T dt. So it's kind of, for better or worse, just to plug everything into the formula and then do the thing. So the only thing you really have to be able to do after you plug everything into this formula is remember how to integrate e to the something times t. And we've done little mini u substitutions like this before. I'll remind you just as like as a different example, right? The integral of e to the 4x dx is e to the 4x divided by 4. Or if you prefer, 1/4 times e to the 4x. And the reason we get that is because of the chain rule, right? If you took the derivative of e to the 4x, you would get e to the 4x times the derivative of 4x, which is 4. And then the 4 would cancel with the 1/4. So the derivative of this is exactly that, which is what we want when we're finding an antiderivative. So whenever you're integrating or antidifferentiating e to the something times x, or e to the something times your variable t, you're going to end up dividing by that coefficient of t. So here is what we're going to get. This constant multiple hangs out, and we get e to the negative 0.08 t divided by negative 0.08. I'm not going to write plus c because it's a definite integral. So we're just going to say we're going to evaluate between 0 and 6. So just as a reminder, right, when you're I'm going to say it one more time. When you're integrating e to the something times t, it's the same e to the something times t divided by that something. You could do a u substitution here, right? You could let u equal negative 0.08 t, but they don't want you to have to do that. So the rest is just plugging it in. Are you guys allowed to use a calculator on your test? Okay. So Nicole, when you ask what t equals, do you mean little t or capital T? Okay, so little t is the variable, right? That actually isn't equal to anything in this problem. It ranges between the values of little t being 0 and little t being 6. So I'll do this problem like I'm not allowed to use a calculator. So the way I finish this problem is I'd probably, like 250 divided, like this seems like kind of, if someone was better, they probably would have given us like 10% to make the math a little easier. But I'm just going to write this as, so negative 250 divided by 0.08. I'm going to bring that over there. And then I'm going to plug in 6. And we get e to the negative 0.08 times 6 minus, I'm going to plug in 0 and get e to the negative 0.08 times 0. And if you're short on time, I would leave it like this. If you have a little extra time, you can do a little bit of simplifying and say, okay, this is negative 250 over 0.08 times 0.08 times 6 is 0.48. So it's e to the negative 0.48 minus e to the 0 is just 1. So you might do some of this in time, but I wouldn't sweat too much, or I would try not to sweat too much the simplification, because he shouldn't expect you to do anything more with this, really, if you don't have a calculator. Yeah. So for these annuity problems, it's really just plug in the information. So we could ask another one, but it's the same work. So let's do one more, just kind of, and I'll just make something up. Sure. So let's say we had something like C of T. I'm gonna make the number super nice. C of T is $1,000. The capital T is 5 years, and the interest rate is 20%. Which is 0.20. One thing I will caution you about, which I've seen the mistake happen too many times in my lifetime, is when you're changing a percent to a decimal, if it's like 5%, it needs to be 0.05, right? If it's a single digit percent, you need the 0.0 before that number. So just make sure if it's like 3%, you're moving that decimal over 1, 2 spots to get 0.03, not 0.3. This one, on the other hand, is 0.2 or 0.20. So then my annuity amount is going to be, what kind of notation do we use here? Nothing special. So the amount is just going to be the integral from 0 to 5 of my C of t times e to the negative r times t. And then it's the same process. We're going to integrate. We're going to get 1,000 times e to the negative 0.20t divided by negative 0.20, evaluated between 0 and 5. Now, I made the numbers easy here so we could simplify. 0.20 is 1/5. So 1,000 divided by 0.20 is going to be 1,000 times 5. Right. I like fractions when they work out to be fractions. So this is really negative 0.20 is negative 1/5. We got e to the negative 0.2t. And we don't really need that 0 there. From 0 to 5. Divided by 1/5 is like multiplying by 5. So this is really negative 5,000 times e to the, plug in 5 and you get negative 0.2 times 5. Plug in 0. I'm just going to write 0 because negative 0.2 times 0 is 0. So simplifying, you get negative 5,000. Again, I think this is fine. Maybe you should change the e to the 0 to 1. Okay, negative 5,000 times e to the 0.2 times 5 is just 1. So e to the negative 1 minus e to the 0, which is 1. And then you could distribute the minus sign and write this as 5,000 times e to the negative 1 plus 1. Or even better, 1 minus e to the 1. Again, what I'm doing right here is not that important. You should probably stop like here, or would change that to a 1. But again, I will kind of try to stress, if you're limited in time, try not to worry too much about the simplification, especially since you don't have a calculator. Let's kind of talk about consumer surplus as well, because it's very much, it's very similar to what's going on here. Maybe not exactly similar, but the formula, at least to me, looks kind of the same. Although I will say, is it on this? I know I said it, but I don't actually see it on this study. I think was the consumer surplus coming from the Merck's side of things. It's okay if it was. I'm just curious. Pham. Okay. All right. Well, let's look at one anyway. So, where'd you go? I have some examples here. Sorry, 1 sec. It's hard to keep track of where everything is. Yeah. Okay. So let's say we have this kind of thing. So we have a demand function. And don't worry, we'll get to the. So the demand function is p of x equal to 50 minus 0.5x. Q of x is the supply function. It's 0.125x. And so define consumer surplus. And again, I would never know these formulas. Right? These are not things you should memorize. These are things you should look up in the book. The formula for consumer surplus is the integral from 0 to whatever constant value, so to the equilibrium value, which we'll find in a minute here, of your demand function minus the price. so let's actually kind of, and then we'll talk about the producer surplus one as well. So what are these things? Well, sorry, this is the demand function, this is the surplus, or the supply function. So we know one of the things so far in this. We know that this is going to look like the integral from 0 to something of the demand function, which we know is 50 minus 0.5x minus the price, which we'll figure out in a second here. So there's two things to fill in: the equilibrium value, right, the upper limit of integration here, and the price. And both of those are found by figuring out where the demand function and the supply function are equal to each other. So I'm going to set P of x equal to Q of x. So in doing so, I get, let's see, 50 minus 0.5x equals 0.125x. I'm going to add this 0.5 to both sides. So 50 equals 0.625x. I'm going to divide both sides by 0.625. I am going to use a calculator. I don't think it's terrible. So I do that. 50 divided by 0.625 is 80. So x equals 80. So 80 is the equilibrium value, right? It's the number of units produced where the demand function is equal to the supply function. And then we need to find the price. Well, the price is what these are equal to when you plug in that value. So if I plug in 80 for x, I can pick either function. It's going to give me the right value. I plug in here, right? So P of 80 is 50 minus 0.5 times 80. 80. Half of 80 is 40. 50 minus 40 is 10. So the number of units at equilibrium is what goes as your upper limit of integration, and the price at the equilibrium is what goes over there. And then the rest of it is integrating. So right, the rest of this is not solely the hard part. I would simplify my integrand, right, is the integral from 0 to 80. 50 minus 10 is 40 minus, I would prefer a fraction here, 1/2 x. That's a 40, by the way. And so I get, let's see, 40x minus 1/2 x squared over 2, so x squared over 4 from 0 to 80. Plug in 80 and you get 40 times 80 minus 80 squared over 4. Minus 0 minus 0. 40 times 80 is 3,200. 80 squared is 6,400. Divided by 4 is 1,600. So you get 1,600. And then the producer surplus formula is very much the same, just slightly different. So instead of being the demand function minus the price, it's the supply function minus the price, right? No, sorry, it's the price minus the supply function. So trying to keep the orange off of that eraser. Make this eraser my orange pen eraser. So I know there was a question about this consumer producer surplus stuff before, and I think the hard part before was that it wasn't clear what the what either the price was or the number of units was. I think the number of units was given, and you had to plug that into the function to get the price that goes there. So let's do the same thing for producer surplus, right? Yeah. So producer surplus, same kind of formula. It's still the integral from 0 to the equilibrium price, but now it's the price, the equilibrium, not price here, the equilibrium number of units, and then it's the price minus the supply function, right? Yeah. So that's going to look like, so the number of units is still the same as it was before. The price is still the same as it was before, which I don't remember what it was. I think it was 10. It was 10. Minus, and then the supply function is 0.125x. By the way, 0.125 is 1/8. So I'm just going to write 1/8 of x. And that's it. And then you integrate. So we get 10x minus x squared over 16 from 0 to 80. That's going to be 800 minus 80 squared over 16. 80 squared is 6,400. 64 divided by 16 is 4. So 64 divided by 16 is 400. I was worried for a second it was going to come out negative because, just one technical, because it should always come out positive, but it definitely came out positive. The supply function, let me double check. I might have made a mistake. You're right, it was 0.125x. Good call. Thank you. So let's actually, no, yeah, I had that. Yeah, it was 0.125x. Yeah, right. Usually the demand function and supply function should have something to do with the number x. Although I guess they could not, but that seems unlikely. All right, so I think this is it as far as consumer demand or producer surplus and consumer surplus, but do you guys have any more questions about it before we move along?
Does it matter what function we plug, or how did you get the 10 again? Did you make it equal or did you plug in 80?
So the way I got the 10 was I set the demand equal to the supply. And that's always how we find the equilibrium price. It's the price.
No, I meant the 10, sorry.
Yeah, that's what I'm saying. Oh, sorry, the 10.
Yeah.
Yeah. So,
no.
so that is the equilibrium price. It's the price you get by finding the equilibrium number of units and then plugging that back into either function.
Okay, so okay, thank you.
If I plugged in 80 here or here, it should give me 10. Because this value, so right, this is if you ever take Econ 1A or 1B, I forget which one, you'll definitely talk about this a lot, where the demand and the supply are equal to each other. And where they're equal to each other, the price should be the same, and the number of units produced should be the same as well. So that's kind of what's happening here. They're trying to find a place where it makes sense to where the people want as much as being produced, and what price will that be. Yeah, there's not a lot else to say about this. Again, there are formulas that just kind of I would never memorize. I would look up every time. But so here's the thing I could see if you did want to memorize them, remembering that it's 0 to the equilibrium value, and then it's the difference between the demand and the price, or the supply and the price. But I could see accidentally subtracting in the wrong direction. And if you did that, you would end up getting a negative number. So if for some reason this comes up and you have to do it, and you have to memorize it, which seems stupid. But if you end up getting a negative number, what I would suggest doing is flipping the order of subtraction, because maybe that's what you got messed up when you're doing it. That's all I want to say about this. Let's move on to average value. And let's take a look. So let me look in the book for some good example questions, just because it's easier to look in the book for questions than come up with them on my own. Although average value is, not too terrible. I'm right in this section. Makes sense, I believe. I was in the right section anyway, sorry.
Could we do an example from his practice?
Sure. Is there an average value, or are we talking about something else?
Yeah. Sure. It's find the average value of the function f of t is equal to t.
Oh. Huh? Okay. So the whole thing with average value is you're just finding the integral and then dividing by the length of the interval. So here's the function, right? The function is f of t equal to t e to the t squared, right? On the interval, oh man. So first of all, I guess it doesn't really matter. Usually normal people, not that he's not normal, but typically when you write the interval of integration, you write it as a closed interval with brackets, not as an open interval with parentheses, but whatever. So I want to find the average value. So the average value of a function is just the area that's under it divided by the length. So you're just going to find the area divided by the length of the interval, which is going to look like the integral from 0 to 10 of t e to the t squared dt divided by the length of the interval, which is just 10 minus 0. So really, average value is just like one tiny extra step after integration. You're still going to do the integral as usual, and then once you found the area under the curve, you're just going to divide by 10. So that's good. So when you're finding average value, that's important to remember. It's really not any harder. You just have to remember what it means. So doing this interval, it does take some work. So usually people write, instead of writing it as all divided by 10 minus 0, they usually write times 1 over 10 minus 0 on the front. So you would see someone write this as 1 over 10 minus 0, or b minus a, times the integral from 0 to 10 of t e to the t squared dt. Now, personally, when my integration is complicated and it's a definite integral like this, I would prefer to do an indefinite integral to the side. Does that say area over length? It sure does. Except somehow I put an e at the end of length because I don't know why. There, now it actually says it. So off to the side, I'm just going to do the integral of t e to the t squared. And I thought this pen, I'm going to use that. That's the wrong pen. My trash pen. Okay. So for the integral of t to the t squared, we have to do a u substitution. And I have to let u equal t squared. Well, I don't have to, but I'm choosing to let u equal t squared for the normal reasons. It's stuck inside some other function, right? It's in the exponent. And more importantly, its derivative is also there. Right? The derivative of t squared is 2t. So du is equal to 2t dt. Oh my God, sorry. So this board feels like it's too far away. Okay. So then 1/2 du is equal to t dt. And I can rewrite my integral. Well, there's my t dt. That's going to become my 1/2 du. And then e to the t squared, that's just going to be e to the u. So I get 1/2 e to the u, because the integral of e to the u is e to the u. And then I get 1/2 e to the t squared. So the integral of t e to the t squared is 1/2 e to the t squared. And the derivative of this would definitely be, well, the derivative of 1/2 e to the t squared would be 1/2 e to the t squared times the derivative of the t squared, which is 2t. The t's cancel, you get the t. So the reason I do that is so that then I can just say, okay, I know what the antiderivative of this is. Got my 1 over 10 here. And then the antiderivative of t e to the t squared is 1/2 e to the t squared. From 0 to 10. So I would probably say 1/2, 1/10 times 1/2 is 1/20th. And then I'm going to plug in 10 and get e to the 10 squared minus I plug in 0 and get e to the 0 squared. This is looking like 1 over 20 times e to the 100th power minus e to the 0, which is 1. So it's looking like it's the second choice. You totally could. So the other way you could do this, which I was avoiding, but you totally could, is you could instead say, let me do the other side here. Be equally fine to say, you know, we had and that was our integral. And if we do the same substitution, u equals t squared, 1/2 du equals t dt. We replace this. So again, my t dt gets replaced with a 1/2 du, and this is e to the u. And then instead of integrating and flipping back to t, you can change your u values to t values. Sorry, you can change your t values to u values. So if t equals 0, well, if t equals 0, u is t squared, So u is also going to equal 0. And if t equals 10, u is going to equal 10 squared, which is 100. So then we can say this is 1/20th. The interval of e to the u is e to the u from 0 to 100. And then just plug in those values and get the same thing. We get 1/20th times e to the 100 minus e to the 0, which is exactly the same as the other thing there. So either way, it's fine. Let's do one more just to kind of make sure it's super clear. But again, average value hopefully won't be too terrible. Let's do this one. I do feel like, especially with this question, it seems like a question he would ask with a u substitution. So I'm gonna, yeah. So let's see, what can I do that's not too terrible? The integral from sure. Sorry. I should let me rephrase this question. So so for f of x equal to this, find the average value of this function on the interval from 0 to the cube root of pi over 2. And if you see a messy, oh sure, I can go back to the other side for a second. If you see a messy limit of integration like that, it's usually a good sign that things are going to turn out nicely eventually. I'm having trouble using my straw here. I'm out of water, that's why. Is this sufficient? Okay. So go ahead and set up the interval for this, for the average value. I'm going to ask you guys to do that while I go refill my water real quick. So set up that interval and think about what u substitution you make. Yeah. As an aside, I know for the Mercs folks, you guys have started talking about improper integrals. I definitely do intend to make a couple of videos about those as well this afternoon. I imagine we might not end up talking about that in possibilities because I know the Pham people definitely haven't started talking about that yet, and it's kind of a weird topic to start talking about if you haven't seen it yet. Okay, so here's what this should look like. So just the setup should look like 1 over this minus this. And even though I know -0 doesn't really need to be there, I might still write it like this on the test just so the teacher knows that I know what I'm doing. And then I'm going to integrate from 0 to the cube root of pi over 2 of this function, x squared cosine of x cubed dx. Okay, so clearly there's a u sub here. The u sub is u equal to x cubed. So u is x cubed. Du dx, right? The derivative is the derivative of x cubed is 3x squared. Really want to remind you guys, when you're doing a u substitution, you find du by taking the derivative. And then I'm going to solve for, I have a 1/3 du equals x squared dx. There's my x squared dx. And that's going to become my 1/3 du. And then x cubed is just going to be u. So I'm going to write this as 1 over the cube root of pi over 2. I know it's not a nice number, but it's a number. And let's go ahead and change limits of integration. So if x is 0, u is going to be 0 cubed, which is still 0. well, gosh, okay, I can make it 0. And if x is the cube root of pi over 2, then u is going to be the cube root of pi over 2 cubed, which is just pi over 2. And then my new integral is going to be 1/3, which I usually put on the outside, but I didn't have enough room, times cosine of u du. All right. So the rest of this shouldn't be too terrible. So I'm going to rewrite this as 1/3 times the cube root of pi over 2. And when you're multiplying something by a cube root, make sure that cube root looks like it's the cube root and not like another 3 multiplying. And then the integral of cosine is positive sine. We've got times sine of u between 0 and pi over 2. So that's going to be 1/3 times the cube root of pi over 2 times plug in pi over 2 for sine. So I factored this out. I'm thinking of this as this times all of that. So I don't have to write this more than once. Sine of pi over 2 minus sine of 0. Sine of pi over 2 is 1, sine of 0 is 0. So I end up with this times 1. So this is my final answer, which I wish I had more room to write. So I end up getting that my average value, let's write it up here, is 1/3 times the cube root of pi over 2. So that's how average value works. It's not too awful. It's really just integration and then dividing by the length. What does the last sign have? You mean down here? Yeah. So that's a sine of pi over 2, which is 1, and sine of 0, which is 0, right? So I just plugged in these limits of integration, 0 and pi over 2.
Can you explain how you got rid of the cubed root on the pi over 2?
Yes. So what I did was I changed the limits of integration, right? So this is my good green pen, hopefully. So these were x values, right? This is x equal to 0 and x equal to the cube root of pi over 2. So if x equals 0, u is going to be x cubed, which is 0 cubed, which is 0. And if x equals the cube root of pi over 2, u is going to equal x cubed. So it's going to be that number cubed, but the cube root cubed is just the inside stuff. So these aren't x values, these are u values. Because if I'm integrating with respect to u, I can just leave them that way. The other option would have been like what we did the first time. It would have been to get sine of u and then go back and plug in and say, oh, I have sine of x cubed, and then plug in 0 for x, and the cube root of pi over 2 for x, which then would have gotten cubed and still become pi over 2. Either way is fine with it. So when you have a definite integral with a u sub, there's always this question of, or this choice of, do I want to change my limits of integration to the other ones and then just leave it in terms of u, or do I want to change it back to x? Usually I'm in favor of doing it this way, where we change the limits of integration. All right, let's see. So let's move on to disk and washer method. So I feel like I did this one before, or one similar to it, but it's a good question anyway. Let me actually ask before I get going too hard here. Have you guys been doing disk and washers rotated around the y-axis or just the x-axis? Both, okay, all right. So here's a question. I think I did the video on this one already. I'm gonna do it again anyway, because it's the kind of question I would want to ask on a test, because I think it makes a student, well, yeah, he could ask this one. It would be, no, it's a fine question. It's just, it's kind of hard. So let's say I have so I want to find the volume of the solid obtained by revolving the region bounded by, right? There's a lot of words I'm not going to write. So you've got a region, it's bounded by the following functions. By the way, Craig, I know Craig, you're probably not watching right now, but if you're watching later, Craig, this is an example of kind of what you asked about in the discussion, although I will do more of them later. So my functions are going to be let's see, y equal to 0, x equal to 0, which are just the x and y axis, y equal to the natural log of x, and y equal to 1. So the region bounded by this revolved around the y-axis. Although it's not an absolute must to draw it, I do think you might want to draw it. I mean, so this isn't terrible to draw. I would draw the constant ones last. I'm always going to draw my function one first. So y equals natural log of x. Looks like this. Intersects the x-axis at the point 1, 0. Okay, so I've got that function, and then I've got y equals 0, which is just the x-axis. Right? So there's y equals 0. I've got x equals 0, which is the y-axis. I've got y equals 1, which is a horizontal line right there. So be careful. People can kind of confused when you have multiple functions that are bounding your region. You have to pick the region that is bounded by all of the functions specified. So this region down here, although it's not really enclosed, wouldn't be the right region because although it's got y equals 0 and x equals 0 and y equals the natural log of x as boundaries, it does not have y equals 1 as a boundary. So we have to pick this region here, which has all 4 of these functions as actual boundaries. So we want this region, so we want the volume of this shape. We want to find the volume. All right, so we're going around the y-axis, which means we need to use horizontal strips. Or is that the way I think about it? So I'm taking a horizontal strip at some height y with some thickness dy, and I'm rotating it around the y-axis. And I'm getting a shape. I have done this before. I'm getting this disk shape. And the volume of this disk very generally is pi times the radius squared, that's the area of the circle, times the thickness of the disk, which is dy. So we need to do 2 things. We need to find out what the radius is there, because the radius varies. The radius is smaller, depending on how, or smaller right down here, the radius is just the length of 1. Up here, the radius is much larger. So the radius is a function of y, right? It depends on how high or low we are. And it's usually just the function that the thing is touching, right? This strip has a length of touching this function minus 0. Okay, I'm sorry. So what's that function? Well, I'm going to write the wrong thing for a second. The function both is and is not the natural log of x, meaning that's the right function to use to think about. That is definitely the boundary function, but it's the wrong variable, right? I can't integrate the natural log of x with respect to y. I need the variable here and the variable here to match up. So I have to say, oh, well, if this function is y equal to the natural log of x, if I exponentiate both sides, e to the y equals e to the natural log of x, which is x. So my function as a function of y is x equal to e to the y. So that's actually what's going to go there. And I will mention also, we should never be integrating natural log of x without integration by parts. So if you see any kind of natural log of x thing, you need to fix it somehow by rewriting it as e to the y. Okay, so that's the volume of this disk, and then I'm going to add up all the volumes of the disks by integrating. Right, we're going to integrate from the lowest possible disk, which is at y equals 0, to the highest possible disk, which is at y equals 1, of this thing here. I put the pi outside. Of e to the y quantity squared dy. Now be careful here. I've probably said in class that e to the y squared is not antidifferentiable. This is not e to the y squared, at least not the way you think I'm saying it. The e to the y squared means this, right? E to the parentheses y squared. But e to the y quantity squared is e to the y times e to the y, which is e to the 2y. So this actually is totally integrable, and we write it as pi times the integral from 0 to 1 of e to the 2y dy. And then we'll do pi times the integral of e to the 2y is e to the 2y divided by 2 from 0 to 1. We plug in 1 and we get, let's bring out the 1 half. Let's say this is pi over 2 times e to the 2y from 0 to 1. And then we get pi over 2 times, plug in 1, you get e squared. Plug in 0, you get e to the 0, which is 1. And I would leave it like that. We use the disk method here because our region was flush with the axis of rotation. A little dizzy there. Let's do another one where we're going to use the washer method. And I'll try and make this one where we have to do a U sub. Yeah. Let me not do exactly the one he's got on his test here, because the one, oh no, that's a fine one. Yeah, I'm not done with that one, but yeah. So let's see. That's an interesting choice you made. Okay, let's do this. Let's find, so let's say, so here's the region. The region is bounded by, what do I want to do? Sorry, one sec. Y equal to the square root of x, and let me think here. Y equal to x squared over, sorry, I just changed my mind about what I wanted. Oh, that's gross. And I'll do it like that. Is that right? Let me think for one sec. No, I need it being 8. Okay, so I want to find the volume of the, solid obtained by revolving this region around the x-axis. So revolve around x-axis. And again, it's pretty necessary to graph this, or at least have a general idea of what the graph looks like. So you might, and well, we're definitely going to have to find where they intersect. So, right, in contrary to the previous example, here we were pretty much given the limits of integration, right? We were given this whole shape, and we said, oh, we're going from y equals 0 to y equals 1, which is kind of already given to us. Here, no such thing has been done. Right? We don't know what the left must y for x is and what the right must y for x is. So we actually have to set these equal to each other and solve. Now, here's what I will say about this. Especially if you've got a square root. No one's going to make these numbers. Well, no reasonable person would make you have these terrible numbers. What I usually like to say about this is you can typically guess the number that is going to be. So what kind of numbers should I guess for square roots? Square numbers, like 0, 1, 4, 9, 16, etc. So I'm going to plug in a few of those and see what happens. So I plug in 0, I get 0 equals 0. That checks out. So 0 is definitely one of the intersection points. If I plug in 1, I get 1 equals 1/8. No, that's wrong, right? Doesn't work out. Plug in 2, I get 2, why am I plugging in 2? Because I'm not taking my own advice. I shouldn't be plugging in 2, I should be plugging in 4. Plugging in 4, I get the square root of 4 equals 4 squared over 8, which is 2 equal to 16 over 8 is 2. So the points of intersection are probably just 0 and 4. And that makes sense graphically because the square root function looks like this. And this parabola function divided by 8 looks something like this. There shouldn't be any other crossing points. Now, I definitely recognize that might not be a very satisfying way to find this, and there might not be enough work shown. So the way you would actually solve this is you'd set these equal to each other. You'd square both sides. The issue with squaring both sides is sometimes you introduce extraneous solutions. So if you square both sides, you get some answers that look weird. Make sure they're actually answers. Squaring both sides leads me to x equal to x to the 4th over 64. Multiply both sides by 64. Don't divide both sides by x, because you'll lose that x equals 0 as a solution. Instead, subtract this over here. So 0 equals x to the 4th minus 64x. Factor out an x. And then you can definitely see that x equals 0, or x cubed minus 64 equals 0, which means x equals 4. So that's the longer way of solving it. But usually, especially with the square root, you can kind of just guess the answers. All right, so we're going around the x-axis. And just like in the previous example, I drew my strip perpendicular to the axis of rotation. And that is always what we have to do to use the disk or the washer method. There's another method we don't learn in 16B called the shell method. That's where you draw the strip parallel, but we don't do that. So always, 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 we're going to draw the strip perpendicular to the axis of rotation, which is nice. So I'm going around this horizontal axis, so I'm drawing a vertical strip. And then, again, the idea is I'm rotating that strip around and getting this donut shape or this washer shape. I just had a donut yesterday. It was really good. It was actually my wife's donut. She shared it with me. She was very nice. So here's my picture. Am I drawing it right? Maybe. I'm drawing it wrong. Sorry. One sec. I always forget to draw these things sometimes. Okay, so there's my washer, right? And the volume of this washer is the area of the big circle, pi times big R squared, minus the area of the little circle, pi times little r squared, right? That's the area of this washer, the big area minus the area that's not there. And then times the thickness, which is dx, right? This is a small little width of x there. So now our job is to find big R and little r, and the big radius is just the function that's further from the axis. So looking at the picture, the big radius is definitely the square root function. So the big radius is the square root of x, and the little radius is the other function. It is x squared over 8. If you hadn't drawn the picture and you wanted to know what the big radius was, you would pick a value of x between the limits of integration. So something that's between 0 and 4, not 0 or 4, and plug it in and see what the function is bigger. The best value to pick between 0 and 4 is obviously 1, because I know what the square root of 1 is. So if I pick x equal to 1, I see that the square root of 1 is 1, and 1 squared over 8 is 1/8. And this is the bigger one, so that's the function that's further away from the axis of rotation. So you didn't have to actually draw it like this. So this is going to look like, let's move to the total volume. So the total volume is where we add up all the washers from right here to right over here. So we're going to go the integral from 0 to 4, right? X equals 0 to x equals 4. Factor out the pi. Terrible. Right, because both of these have a factor of pi. And then big radius squared is the square root of x squared, which you should just write x. Little radius squared is x squared over 8 squared. So I end up with pi times the integral from 0 to 4 of x minus x to the 4th over 64. A lot of times these numbers are not going to be nice for volume. And let me erase this here. I'm doing a lot of, I'm dizzy again. That's not good. Shouldn't be getting dizzy all the time. I understand it. Okay, so looking at this, pi. Remember the pi. It's easy to forget it, but make sure you put it there. Antiderivative of x is x squared over 2. Antiderivative of x to the fourth is x to the fifth over 5 times 64 from 0 to 4. So plugging in, I get, let's see, plug in 4, I get 4 squared, which is 16 over 2, minus plug in 4 to the fifth. I don't want to multiply this because I actually see the stuff is going to cancel. 5 times 64 is 4 cubed. And then if I plug in 0, I get 0 minus 0. Make sure that you at least mentally check that plugging in 0 gives you 0, right? In a lot of examples, like this previous example, plugging in 0 didn't give us 0, it gave us 1. So make sure you're not just assuming that 0 gives you 0 all the time. So here,
if it didn't equal 0, would you subtract it like within the parenthesis, like where?
So pi still has to distribute everything, but I would do plug in 4, this minus plug in 0, it would be 0 squared over 2 minus 0 to the fifth over 5 times 64. So you'd have to have subtraction there and then minus that thing there.
Okay.
Clarify?
Yeah, thank you.
So I'm going to simplify this. So I will point out, if you're low on time, leave it like this. Maybe you could do, this is pi times, right, 16 over 2 is 8 minus this number here. But I see that 4 to the fifth over 4 to the third does simplify to 4 squared over 5. And we can simplify this as pi times 8 minus 16 fifths. And you can either get a common denominator, but dividing by 5 actually isn't terrible. 16 fifths is 3 1/5 or 3.2. So you can do 8 minus 3.2 is 4.8. Or you can do the common denominator. 8 times 5 over 5 is 40 over 5 minus 16 over 5. 40 minus 16 is 24. So you get 24 pi over 5. I'm going to say it at least one more time, probably more times. If you're short on time, leave the simplification, right? Leave it at, I plugged in, I got an answer. Even if it looks gross, you've still done most of the work that's important. And I would like, So I know I say that, but then looking at his practice here, he clearly is giving you multiple choice problems where you actually have to figure out what the integral is. So if you have a problem where you just have to show your work and get to some answer, then I'd say leave the simplification in. But if you have multiple choice questions, you clearly actually have to finish it off and try and figure out what the answer is. So hopefully there's some partial credit for showing your work, I would like to imagine. All right, well, so great. How fair? Let me see. I know there was something else I wanted to mention. Let me look at his practice for one sec here. Okay, I don't see. That's a good question from Jalissa. I don't see any questions about the midpoint rule, so I don't think I will cover that right now. He's doing some weird, not weird, very typical for what this book does with the midpoint rule. So I guess I should ask, are there any other types of questions from his practice that you would like me to talk about? I can certainly do more disk washer if you want, but I know there are other things on here that you might want me to mention. I think, yeah. So I'm gonna do a couple questions. So problem 6 on his exam here, logarithmic differentiation. I do feel like I should do a couple examples of that just to kind of remind you guys of how it works. I'm not gonna do the same exact ones so that you can have those for practice later. But let me give you 2 different ones because these are exactly the kinds of questions that I would ask on a test, and they're not terrible if you know what you're doing. So let's say we had something like, we'll do a fraction one first. Yeah, he's doing it. He's doing a lot of what I do. So let's say we had y equal to something like x to the 4th times the square root of x cubed plus sine of x all over, we made it too easy, x to the 6th plus 9 squared. I would probably have another factor on the bottom, but whatever. So yeah, so he definitely specifies you have to use logarithmic differentiation on this problem, right? I've definitely asked questions on an example like this before and said find the derivative. The intention being to use logarithmic differentiation. He's actually saying you have to, which is good because that's the way you want to do this problem. So you want to take the natural log of both sides. And the whole point, and I'm going to write this as x cubed plus sine of x to the 1/2 over x to the 6 plus 9 squared. The whole point of taking the logarithm of the right-hand side is to use the log rules to break this up into multiple pieces. Sure, I can definitely do that next, Abby. So I'm going to break this up. Now here's the thing that always happens. All the pieces on top, or all the factors, I should say, on top, end up in their own logarithm with a positive coefficient, and all the pieces on the bottom with a negative coefficient. So this is going to break up as the natural log of y equals the natural log of x to the 4th plus the natural log of x cubed plus sine of x to the 1/2 minus the natural log of x to the 6th plus 9 squared. And then you can differentiate right now, but I think it's better to bring down the powers. So I'm going to write this as the natural log of y equals 4 times the natural log of x plus 1/2 times the natural log of x cubed plus sine minus 2 times the natural log of x to the 6th plus 9. And then we differentiate both sides. You have to remember, the derivative of the natural log of y is 1 over y times the derivative of y. On the right-hand side, the derivative of 4 natural log of x is 4 times 1 over x. The derivative of 1/2 times natural log of the stuff is 1/2 times the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, which is 3x squared plus cosine of x. Minus 2 times the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, which is 6x to the 5th. And finally, there's one last step. You have to multiply everything by y. Well, it's actually kind of 2 steps. To multiply everything by y and rewrite what y is. So I'm going to say y prime is equal to y times all of this. And I'm going to simplify this a little bit. 4 over x, mostly just for space, plus this can go on top. 3x squared plus cosine x over 2 times x cubed plus sine x. Minus 2 times 6 is 12x to the 5th over x to the 6th plus 9. And you can do this in 2 steps and say this is y times all this, and then but you can replace y, or you can just say I know what y is. Y is all that. It's x to the 4th times the square root of x cubed plus sine x all over x to the 6th plus 9 squared. So that's the process for one of these long ones, or one of these ones where you've got, gosh, I'm getting dizzy every time I stand up. That is kind of maybe a little worrying. Anyway, this is how we do this kind of one. The next one after that is similar but a little bit different. Sorry, come on. Okay, so just again, I'm going to try and make up a study guide for you guys. I will make a study for you if you guys get it posted. And I'll try and make short videos kind of going through all the questions as well as other videos you guys were asked about. So area between two curves. Here's what I would say first of all. If you do it and you're sure you've done it right and you get a negative answer, it probably means you've subtracted the functions in the wrong order. So in general, if I want to find the area between two curves, f of x and g of x, it's typically the integral from a to b of f of x minus g of x dx. Or g of x minus f of x. And now what some people do is they just say, well, I'm not going to worry about the order and take the opposite value, which is technically correct, although your professor might not want you to do it that way, which I guess I understand. Yeah. Although I will say, if someone marked you wrong for doing it this way, unless they specifically said you need to tell me which function is larger, it wouldn't be right. But it's still a good practice to figure out which one is bigger. So we can actually do it for, oh gosh, there's lots of functions we can do. Let's say f of x is equal to, sure, I'm going to do this one, the square root of 9x, and g of x is equal to, what have I got here, 9 x squared over 9. Sure. Now, to me, obviously, the way I set this one up, it looks like 9 is probably going to be where they intersect. So how do we know which one goes first? We'll sure. So the way I'm writing this is supposed to be general. It should really just be, you should write it as the top function minus the bottom function. So whichever one is the top is the one that goes first. How do you know which one? Well, I'll show you. So first, find where they intersect. And we can, so we'll do it the long way, because again, it's not always going to be easy, but I would definitely be plugging in numbers like 0 and 1 and 9, because those are easy to take the square root of 0 times 9 and 1 times 9 and 9 times 9. But if we set them equal to each other, we have the square root of 9x equals x squared over 9. Square both sides. 9x equals x to the 4th over 81. Multiply both sides by 81. Okay. 81 times 9x equals x to the 4th. Subtract. So 0 equals 81 times 9 is 9 times 9 times 9. So I might write that as x to the 4th minus, instead of 81 times 9, I might think of it as 9 cubed times x. Because then if I factor out an x, I've got x cubed minus 9 cubed. And I can definitely see that x is 0 or x is 9. You can also have seen it here, right? If I plug in 9, the square root of 9 times 9 is the square root of 81, which is 9. Here, 9 squared over 9 is also 9. You can figure out which one is bigger, which one is the top, which one goes first, by either graphing them both and just seeing, although graphing is not always easy. The usual easier way is to pick a value between where they intersect and plug it in to see which one's bigger. I'm going to pick, so normally I would try and pick something that's easy to evaluate, like x equal to 1. So if I pick x equal to 1, I see that f of 1 is the square root of 9 times 1, which is 3. G of 1 is 1 squared over 9, which is 1/9. In this case, clearly 3 is bigger. If you weren't so good at picking, let's see what happens if you pick x equal to 2. I plug in 2, I get the square root of 18 for f. I plug in 2 here, I get 2 squared over 9, which is 4 over 9. And although I don't exactly know what the square root of 18 is, I know it's definitely bigger than 4 over 9. Right? The square root of 18 is between 4 and 5. 4 over 9 is less than 1. So this is my bigger function. And so then what I'm going to do is I'm going to say, well, I'm going to erase this. I'm going to say, all right, well, this is equal to the integral from 0 to 9 of the top function minus the bottom function. And that's how we would start that one off. To actually do this one, I'm going to write it as 9x to the 1/2 minus x squared over. Oh, I could have made my life easier if I been smart about this. So I was about to do something dumb. Well, maybe not dumb, just less informed. I was about to try and integrate this by doing a menu substitution. But square root of 9x, how could I simplify that? Well, I know the square root of 9 is 3. So I'm going to write this as 3 times the square root of x, which is maybe how I should have written the function in the first place. Now it's definitely easier to handle. This is going to look like the integral from, let's see, 3 times x to the 3/2 times 2/3, right? We're divided by 3/2, minus x cubed over 3 times 9 is 27. 0 to 9. So 3 times 2/3, those cancel, give us a 2. And then I plug in 9, I get 2 times 9 to the 3/2 minus 9 cubed over 27 minus, plug in 0, you get 0 minus 0. Okay, it's pretty gross. We can simplify this. Sorry. So I end up with, let's see, 9 to the 3/2 is 9 to the 1/2 to the 3rd. And 9 to the 3rd over 27 is 9 times 9 times 9 over 27, which I can see, let's see, you can cancel a 9 and a 9, go through the 3 here, I can cancel a 3 and a 3. So I end up with a minus 27 over there, and 9 to the 1/2 is 3, 3 cubed is 27, so I get 2 times 27 minus 27, which is 127. The numbers are not beautiful here, but whatever. So the way, so to kind of loop back around to answer your question again, the way you figure out which function is the first function, the one you're putting there, and then the other one there, is you're just picking a value between new limits of integration and plugging it into both functions to see which one is the larger one. That's the one that goes first. Oh, I did want to do one more question, just to kind of go back to the logarithmic differentiation questions, because the other one he asked you is also a question I would definitely ask, and it is a little bit different than this. This will start off the same way, but it's less about using the logarithm rules to simplify and more about, well, let me just show you. So he's got something wacky looking. That's not so terrible. Let me give you yeah, really that. Why not? Okay, fine. Let's do y equals x to the, I'll make it really fun, x cubed plus sine of x. Sure, why not? So the way you're going to try and differentiate this, again, is by starting off by taking the natural log of both sides. And we know we have to do the natural log of both sides here, because you have an expression where you have both a base and an exponent have a variable in them. He also told us to, but still. Natural log of y equals the natural log of x to the all this. And the whole reason for taking the natural log of this right hand side is you have the natural log of something to a power. That power gets to come down in front. So your natural log of y equals x cubed plus sine x times the natural log of x. You might distribute and write it as x cubed natural log of x plus sine x natural log of x, or you might not. And just, sorry, one thing. Did I give you guys the attendance form, just in case I didn't? There's the attendance form again. I think that's the attendance form. Actually, I'm not sure if I copied that right. Just let me double check. Sorry, I got distracted. Yeah, that is. Sorry, all kinds of things. If you got to go, I totally understand. There's the attendance form for sure. So I'm not going to distribute this. I'm just going to take the derivative. The derivative of natural log of y is 1 over y times the derivative of y. The derivative here, I am going to have to use the product rule. So it's the derivative of this, 3x squared plus cosine of x, times this left alone, plus this left alone times the derivative of this, which is 1 over x. And then the last step, or the last 2 steps, is to multiply both sides by y, and then replace y with what it's equal to. So I get y prime equal to y times all this stuff. 3x squared plus cosine x times natural log of x plus x cubed plus sine of x over x. You might simplify it. I don't think you really need to. And then all of that times y, which is x to the x cubed plus sine of x. So that's how you do a problem like that. All right, I think that's all I've got for today. Again, I'll definitely get some stuff posted. I'll shoot out some emails once I have it posted. And if there are other things you specifically want to see, definitely we can do more review Thursday. I will say Thursday we can do more review, but I don't want to completely ignore the Mercs people. So Mercs people also, if you have things you want to see, I definitely already am planning to do some improper integral videos, but if there are other things, let me know. And yes, we can definitely review more on Thursday. Try to think of specific questions you have for Thursday. All right, that's all I got. Let's call the class.